Hello, Mr. Aaron, Mr. Ryan. Have a nice weekend, right? Good?
It hasn't been the weekend yet.
Okay, Friday night, okay. So we have talked about that problem, right? The graph problem, undirected, unweighted graph. We given a unweighted, undirected graph, and we are initially at 0.
Okay.
Yeah,
Boo.
something like that, right? And then we have edges connecting to some of them. So this is an undirected, unweighted graph, and we given the edges, list of edges. And we also given a list of nodes that we are forbidden to go there, and then we are initially at node 0. For example, like we forbidden to go to 1, we are forbidden to go to 3. So we want to find out how many nodes we can visit under such circumstances. So these two nodes we can't visit, so we can only visit 1, 2, right? Okay. So we talk about 3 algorithms: breadth search, depth search, and union find on using the disjoint set. Okay.
Yes.
So what kind of data structure we use to remember the nodes we have visited? Hash set, yes, because we need to remember the nodes we have visited. Otherwise, we will trap on the repeated nodes. Okay, so let's revisit the breadth search. We use the breadth search. What kind of data structure we use to implement the breadth search? VQ, double NDQ. Okay, so basically we have a queue. We initially put the node 0 in, and then we take it out, DQ, from the left hand side, and then we append the neighbor nodes of node 0. The neighbor nodes are the nodes that this node connects to. Okay, so we build the graph. We have built a graph using the adjacent list, so we know the number of nodes. We know the vertex that the node 0 connects to, which is the 1, 2, 3. Okay, 1, 2, 3. But 1 and 3 are in forbidden list, so we don't push it. We don't append it. We don't enqueue. Okay, so instead we only enqueue the vertex 2. Okay, so we put a 2 in, and then we take it out. And the neighbor nodes of 2 is 0, but we have visited 0 before, so we stop here. We count the number of nodes in the hash set, in the nodes we have seen, which is the number of the nodes that we can visit from node 0. Define breadth search. In the beginning, we call it root. If the root is in a restricted set, okay, then we return 0. We have a scene table hash set. At the beginning, we are at root. And we need a q equals dq. Root, we put the initial root in, while q. Okay, so we can, as I said last time, we can take one node at a time, or we can take all the nodes and then append the neighbor nodes of the current order nodes in the queue, right? Okay, so what's the difference? So if I take one node at a time, then we just take one node at a time. But if I take everything out of the queue, all the nodes in the queue belongs to the same distance, same level, right? It's just like binary tree, remember? Binary tree. 0, 1, 2, 3, 4, 5, 6, right? This is the perfect binary tree or full binary tree, okay? This one, right? So look, if I take everything out, then we have only 0. Then we take it out. What's the kit of 0, 1 and 2? Okay, and then I put the 1 and 2 in. Now I take 1 and 2 out. I take all the nodes at once. And now what's the neighbor node? What's the kit of 1 and 2? 3, 4, 5, 6. Do you notice? Do you notice? So at any time, the nodes in the queue belongs to the same level. Okay, it's the same thing here, okay? So we can take one out or we can take everything out, okay? Let's take one out at a time. Current equals q dot pop left. Then we need to check, right? We need to check the neighbor nodes, which is the, for n in G is the adjacent list from the graph. GC is the list of nodes that the node C connects to. So basically there's an edge between C to N. C to N, right? So if N is not in R, also N is not in scene. We haven't seen this node before. We haven't visited this node. Also, we can visit this node, right? It's not in the forbidden list. And then we just have to queue.append. Then we push it back to the queue. And then we have seen this node, so we mark it as seen. Okay, and then return the length of the hash set, because this is the answer we're looking for. The key thing here is that we're using the DQ, WNDQ, and we use the pop lab. We take it from the left hand side. Okay? What happened if I change the queue to stack?
And do you like bubbles or pancake?
I don't mind.
Okay, Eric, what happened if I change the queue to stack and instead of pop, for the stack, it's always popping from the right hand side, right?
You know, I think waffles are better than pancakes because I just find waffles funny.
Stop, okay. Okay, let me finish, okay?
You haven't made that long.
Yeah, it managed. Doesn't make me laugh. Okay, come on, stop it. Okay, we talk about the breadth search. The key thing here of using breadth search is that the DQ, WNDQ, and the pop left. And pop left, right? Why is pop left? The queue is first in, first out, right? When we put the items in, we put it on the right hand side. We take it out from the left hand side. It's just like a queue, first in, first out. Okay. And what's the stack? For the stack, what's the order? First in.
First and last out.
That's the stack. Okay. So. Yeah.
But
Okay. So for example, like if we put the items 1, 2, 3, so like 1, 2, 3, right? Then we take it out. What's the order?
Bang.
What's the order? What's the order?
3 to 1.
You put this in and then you take it out, right? You put 1, 2, 3, and then you take it out. It's 3, 2, 1. Okay.
Bang.
So what happens if I change the queue, DQ, to stack, which is the list, and instead of pop lab, we just need to pop. Okay. What happened? Can you imagine? Can you try to guess what happened? We talked about this actually once before. What happened if I change the breadth search in the by using the queue to a stack, and for the stack is pop, not the pop left. Okay. So what happened?
The result is the same.
The result is the same. Yes, that's good. The result is the same.
So nothing.
But what's different?
Nothing.
What's different? What's different? The result will be the same. Yes, obviously.
It doesn't matter available.
It doesn't matter, but something has changed.
It doesn't matter available code is available result.
Are you trying to be Scottish? Okay, what's the difference? What's the difference? If I change what's the difference between the queue and the stack? First in, first out. What's this? If I change the queue to stack? What's changed? What's changed here?
First one is gonna be the last one.
Yeah. So what is this?
Keyless slack.
The order, the traversal order, right? The sequence
It
is
doesn't
different.
matter.
Yeah.
It doesn't matter.
Yeah, it doesn't matter, but the traversal, the sequence has changed. Okay, so the result is the same regarding the number of nodes. The answer, we can still get the answer, but the order of traversal, the nodes, is different. What kind of order is this? Is this depth search? It might be a little bit difficult to see from a graph, because graph has lots of these edges which are connecting to each other, right? Let's take a look. Okay, 0, 1, 2, 3, 4, 5. Okay, let's forget about the forbidden list. Let's just take a look at these nodes. For example, 7. Okay, just these. This is 6. This is undirected, unweighted graph. What's the order of depth search from 0?
0,
1, 2, 4, 6, 3, 5.
Okay, or 2, 7, 5, 4, 6. It doesn't matter as long as you.
Where's the 7? Where's the 7?
Or 6. Okay. So what's the?
Bang.
Okay. How about let's just consider the nodes in sorting order so we can compare. Okay. So what's the sorting order? What's the?
In order.
No. Look, 0, 1, 2, 3, 4, 6, 5. Right? Okay. Yeah. 0, 1, 2, 3, 4, 6, 5. This is depth search. How about breadth search?
Huh?
How about the breadth search?
0, 1, 2, 3, 4, 5, 6.
0.
How's that deficit?
0, 1,
0, 1,
2, 3,
2,
4, 6, 5.
3, 4, 6, 5. Yeah?
No. I thought 0, 1, 2, 4, 6, 3, 5.
0, 1, 2, 3. 3 and 4, it doesn't matter. Let's. Ryan. Come on, please. Come on.
I thought you said it was like left note.
Yeah. Okay. What? Yeah. What I'm saying is that let's consider the nodes sorted for the from smaller to the biggest for the same neighbor nodes. Okay, so 2, 3, 2, 4. 3 comes before 4. Okay, yeah. Let's make this assumption, but actually you are right. We can visit 4 or 3, depending on the context. Okay. So do you understand? This is depth search. Okay. Yeah.
Yeah.
How about breadth search?
0, 1, 2, 3, 4, 5, 6.
0, 1, 2,
3,
3,
4, 5, 6.
5, 6, yes. Okay? 0, 1, this is distance 1, right? 1, 2, distance 1. And now we are 2. 2, then these 3 nodes are distance 2, so it's 3, 4, 5. We consider, increasing order, and then 6, okay? Okay, so now, interesting part. If we change the queue to stack, so what happened?
Brains.
Okay, now look, this is a stack, right? Okay, 0, obviously we put a 0 here, right? We take it out. What's the key of 0? 1, 2, right? 1 and 2. 1
I'm
and
the
2.
kid of dad.
So we put a 1 and 2, right? In increasing order, right? Let's take a node, next node out, which is 2, right? So put a 2
3,
here.
4, 5, and then
2, what's the key?
3, 4, 5.
Yeah.
3,
3, 4, 5, okay? And then we take a 5 out, right? Okay, what's the key of 5? Nothing. Okay, actually 2, but we have seen this 2 before, so we don't put it back to the stack. And then 4, 4. What's the key of 4? 6, right?
6.
And
I
then,
got it.
and then we take it off, 6. And then, next, 3, 1. Okay, so what's this order? 0, 2, 5, 4, 6, 3, 1. Okay, 0. Come on. Okay, let's check if it's pre-order. Okay, 0, 2, 5, 4,
6, 3,
6, 3,
2.
1. What's that? What's this order?
Unorder.
Actually, this is depth search.
Unorder.
Is it depth search?
No.
Yes. Yeah. It's kind of. It depends on how we put the nodes in, right? If we put the opposite, right? Why is it depth search? Look, it's kind of one way of depth search, right? Look, 0, 2, 5, right? I go as deep as I can. I come back and then follow the other route. 4, 6, and then come back. 3, 1.
But that isn't as deep as 0.
No. What do you mean?
No, that isn't as deep as 0, 2, 4, 6.
0, 2, 4, 6. I know, but
Yeah, that isn't as deep.
no. This is
You're good.
as deep. Yeah. Remember the binary tree. What do I mean? Here, look. This might be deep. Alright, right. Come on. Alright, right. This is the same. Look. This is depth search. I travel here, and then go back, and then follow another route. Okay, this is deeper. So
Of course it's
it
deeper.
depends. Why is this kind of order? It depends on if I travel these or the branches of the neighbor nodes, right? Remember we put a 1, 2, 3 0, and we put a kid is 1, 2, right? We put a 1 in and 2 next. If we put a 2 in and 1, then it'll be different. Yeah, got it? Okay, so let's take a look at the other one, which is I put a bigger one in. Okay, so 0. Yeah, I put it here. Okay, 0. This is depth search, recursion depth search. This is breadth search. Yeah, this is we change the queue to stack. If we put a 1 smaller node into the stack. Okay, if I put a bigger one in the stack, right? 0. And what's the key? What's the key of 0? 1 and 2, right? Let's put a 2 first and then 1. Okay. What's the key? What's the next to take out? Come on. 1.
What?
What's the key of 1? Nothing. And we take out 2 out, what's the kid of 2? 3, 4, 5, right? And then we need to put the 5, 4, 3. Okay? And then what's the kid? What's the next?
3.
What's the kid of 3? Nothing, okay?
Yeah.
What's the next to take out?
4.
4.
5. 6.
4. And what's the next?
Six,
We need to put a
six.
6 in, right?
Yes.
6. And then,
5.
okay, so 0, 1, 2, 3, 4, 6, 5, right? Yeah? What's this order? It's kind of DFS search, right? Okay, so to sum up, if we change the queue to stack, we get the DFS search, right? Depending on the order we push the nodes, the children nodes, right? The neighboring nodes back to the stack. The order may change. So remember the pre-order, in order, post order, right? This is similar, okay? Okay. That's it for today. Bye bye. Bye.